Today it's an honor to give you this talk. As you can see in the screen, I'm going to be talking about the role of dislocation cells in the hydrogen embrittlement susceptibility of nickel-based alloy, Inconel 718. And I like to acknowledge the work of my co-authors. Actually, it's one of my PhD students, Claudia, and also Son, which is her supervisor. And of course, my boss, Emilio, that you can see in this slide. Actually, he was supposed to give this talk, but he's away, so I'll try to meet the standards. We are a large group based in Oxford now, around 12 postdocs and eight PhD students. That's our building. I think some of you may know it because we have hosted a workshop recently in Oxford. This is our lab. We are starting when we arrived in Oxford a year ago. It was an old office, but we have managed to start doing some electrochemical experiments. We have a TDS, some microtensile stages, a gaseous permission apparatus, and we have recently acquired an additive manufacturing machine. So the motivation of my talk today is that, as many of you know, so I'm gonna rush a bit here, so I have more time for the results. Is nickel-based alloys are embrittled by hydrogen. You can see here some examples of two series of Inconel, where hydrogen is able to reduce the mechanical properties a lot. And we want to know if the same is going to happen when we switch to additively manufacture nickel-based alloys. And of course, it's a necessity to start investigating these new, or not new now, but these more recent manufacturing techniques, because they are pretty useful to manufacture parts with complex shapes and requirements. So the aim of the talk is going to be to assess the hydrogen embrittlement, diffusion, and trapping in additively manufactured Inconel 718. So I'm going to be comparing all the time the rod condition versus the as-printed condition of Inconel, so no heat treatments today. And the specific objectives that I have today is to study how is the absorption behavior in each of the conditions, determine the hydrogen diffusivity at a wide range of temperatures, assess the influence of hydrogen on the tensile behavior, and see which is the role of these dislocation structures, and then perform a trapping analysis using a tool called the TDS simulator. So we can, let's say that we have studied two conditions of Inconel: the rod from a hot rolled and annealed slab, and then the laser powder burst fusion selective laser melted additively manufactured Inconel in two directions. And to do so, we have employed small TDS samples, like these ones, 10 by 10 with a small thickness, and also pretty little tensile samples like dog bone specimens. Okay, so from this slide, we can see straight away the big difference that we have between the microstructures of the rod and the additive condition. We can highlight the columnar grains that are characteristic of these additive manufactured alloys. Well, in the rod, there is not much to say apart from that we have an equiax structure with some carbides and nitrides over there. And for the additive, as I said, columnar grains with a fine dislocation cellular structure in between, like with these dendrite shapes. So what we have done, hydrogen charging, electrochemical technique, because at that time we didn't have the gaseous charging setup established in our lab. So we tried to introduce as much hydrogen as we could, trying to saturate the samples. That's why we chose small thicknesses. And then we performed TDS to do the trapping analysis and determine the hydrogen diffusivity of both alloys. This is actually the absorption behavior, where we can compare straight away the rod versus the additive. Well, actually, I'm plotting here the hydrogen concentration, the total hydrogen concentration versus charging time. So the first thing that could strike us is that we see the additive can absorb considerably higher hydrogen compared to the rod. And that more or less around 7 days of charging at this temperature, we have a pretty homogeneous hydrogen concentration across the thickness of my samples. And this is how the TDS spectra looks like. Actually, we can, right now, only with this data, we can already provide a value for the hydrogen diffusivity at this temperature if we do a very simple fitting. We see there is not great difference in diffusivity, of course, at this temperature between the three conditions. Also, we see the directionality in the additive is not having a great influence. Actually, we can see the results are pretty comparable. But what we can say, as I already advanced in the previous slide, is that with this diffusivity, we do a simple calculation of the hydrogen concentration profile. We see that from 7 days, we more or less have saturated the samples, which are very thin. Then we wanted to perform a hydrogen trapping analysis using Oriani's theoretical, let's say, framework. So we have to determine the binding energy, the trapping binding energy, and the trap density. That's why we use the TDS simulator. That's just an app, a MATLAB app that our group have developed recently, where you can just put the details of your experiments, like your experimental conditions, the details of your sample, your thickness, blah, blah, blah. And you can do a fitting of the experimental curve, and it can provide both the binding energy and the trapping density of your material, in this case, of hydrogen in your material. We are still working on it, but I think the publish is going to be submitted very soon. So it's been submitted, but it's going to be online very soon. So this is how it looked, our TDS curve, as I showed before. I had to decide, and that's something you have to decide, like how many traps you wanna fit, let's say, or how many traps you have in your material. This is always a tough decision because we know there can be many traps with very close binding energies. But I checked the literature. Usually for nickel-based alloys, people consider 2 or 3 traps. So for the sake of simplicity, I said, okay, I'm gonna consider 2 traps. So I performed this fitting, which was pretty good for my purpose of just comparing one condition to the other. And I obtained the binding energy and the trap density for 2 different traps for the 3 conditions. First thing we can observe is that in general, the binding energy was higher for the rods in both of the traps, while the density of traps was higher in the additive condition. And okay, like with the microstructural analysis that we have performed, we cannot really like state that this trap corresponds to a certain microstructural feature and this to the other. I can do some guesses. For that, I think some of my colleagues in the public are going to present data of atom probe, where you can directly see the atom in that feature. So that's, let's say, more useful to do this association. So maybe if we could combine works, it would be really nice. But our guess is that this binding energy is associated to the lattice of diffusion in this Inconel microstructure. And then we have a higher energetic trap that we think for the rod is associated to grain boundaries, or these carbides and nitrides that are like interfaces that we have in the grain boundaries. And then for the AM, a trap that corresponds to the interfaces of this dendritic like cellular structure or the walls. Then regarding the hydrogen diffusivity, we have applied a technique that we have established in our group for both, that works really well, sorry, for both very slow and fast diffusion metals, and actually provides similar values than gas permeation, but it's very helpful because you reduce considerably the scattering of the measurement, and you can measure the hydrogen diffusivity at a wide range of temperatures. Sorry, I have not said the name. Sorry, I'm not come back. Okay, it's isothermal desorption. So basically, you place the sample on the TDS, you keep it at a constant temperature, you have a desorption profile. Oh, again, you have a desorption profile that you can fit, and we have done that at room temperature and then higher temperatures. In this case, up to 400 degrees, which is really challenging when you have a permeation apparatus. So this is how the desorption spectra looks like, or the isothermal desorption spectra looks like. For both, I've just shown some like 2 examples at room temperature and 90 degrees and the fittings. So we can see again, and actually we can see it better here. So this is the diffusivity for the 3 conditions at different temperatures. That in general, the diffusivity of the rod and the additive is pretty comparable. We could say that maybe at lower temperatures, 90 and 22, the AM has a slightly higher diffusivity, but then these differences cannot be noticed at higher temperatures. So if we have data for diffusivity at a wide range of temperatures, we can do an Arrhenius fitting, and we can determine the Arrhenius law. All right, which is really interesting if we want to have the diffusivity at any temperature, and also to compare data with, or to compare our data with the previous data found in the literature. We see a quite nice agreement with what we've seen so far in the literature, and we have determined this Arrhenius relationship for both the rod and the AM. And again here, as we could see in the trapping analysis, that the binding energies were a little bit smaller in the additive condition. We can see energy associated for activation of diffusion in the lattice that's a bit smaller as well than in the rod condition. Then we compare the tensile behavior. This is the part that Claudia did. So, well, I'm gonna just comment on it. We have performed like tensile testing on, of course, like uncharged and pre-charged samples for a duration of between 1 and 14 days, like we did for the TDS specimens. So you can see embrittlement is huge in both cases. And regarding the fracture surfaces, but we see, no effect of directionality again, like happening in the TDS analysis. So not a lot of difference between having the sample in one direction or the other regarding the building direction of the print. Okay, so, and we have intergranular fracture for the rod, and then we have some kind of weird transgranular fracture for the additive that resembles these like cellular structures that we could see in the previous slides in the microstructure. So we can infer that here we are having decohesion along these dendrite interfaces. So basically, we are having accumulation of hydrogen along these interfaces. We could explain these results in base of the trap binding energies that we have measured, of these lower binding energies that we have measured in the additive, that basically indicate, and also the slower diffusivity, that hydrogen is accumulating in this high dislocation density of our cellular structure, and that is provoking a higher absorption of hydrogen, and also a reduction of the binding energy, because we have pipe diffusion along this cellular structure, which is also related to the lower or the higher hydrogen diffusivity in the additive. And we can explain the decohesion of all the internal interface, both in the rod and in the additive, regardless of the charging time, because something interesting here is that regardless of the charging time, we have a lot of embrittlement. So basically what we can see is that we have a very high trap occupancy in all these interfaces, even for small charging times. So we are more or less in this region where we have a trap occupancy close to 1. An interesting event that we observed with a sample that we have tested, so this is the fracture surface. We looked at it initially in the SCN, and we saw these cracks along the dendrite interface in the AM condition. And then 1 month after, we went again to the SCM, and we saw that these small cracks that had initiated in those interfaces had propagated along the interface. We don't know if because there was some residual stresses, or what we know that hydrogen always provokes these delay cracking events, right? So basically, what we can see is that in AM Inconel, the absorbed hydrogen was significantly higher than the rod condition, which agrees with the higher trap density determined in this condition. Then the hydrogen diffusivity is slightly higher also in the AM condition, especially at lower temperatures. hydrogen diffuses and is trapped along cellular boundaries that have high hydrogen coverage, significantly lowering their cohesive strength. And then microcracks are formed at these cellular boundaries, which eventually breach and can merge to grow and propagate along the cellular boundaries, not along the grain boundaries in the case of the AM conditions, causing this intragranular fracture. And then as ongoing work, we are studying the influence of heat treatments on this behavior. So we can also, let's say, gain more insights into the role of these cellular structures. And we are doing some APT to see where atoms are located exactly. Thank you very much. And I don't want to leave without showing that research can also be fun. So this is me when I received the TDS. Some days after I installed the TDS in the lab, some of my colleagues measuring pipelines that we are studying in the lab, and Lore, who presented yesterday, trying to find the interface. And that's all. Thank you very much.